Hello, welcome all. This is going to be your lesson on 4.3 curve sketching, but prior to curve sketching I wanted to talk about two specific problems from last night's homework involving the mean value theorem and somewhat of a relationship to the intermediate value theorem. This is question 12 from lesson 4.2. Took 20 seconds for the temperature to rise from 0 to 212 degrees Fahrenheit. And when a thermometer was taken out from the freezer and placed in boiling water, explain why at some moment, the initial interval, the mercury was rising at exactly 10.6. When you analyze a question like this, explain why at some moment, that's usually a key that you should be applying either the intermediate value theorem or the mean value theorem, because those are about finding times given some sort of change. Since this temperature changed 212 minus 0, which is 212, over 20 seconds, if you were to divide these two numbers, you would get an approximate answer of 10.6. Now, why would this be an intermediate value theorem problem? The key to doing this is to kind of look specifically at the units. When you're working with degrees Fahrenheit and you're working with seconds, but the question is asking you about a rate, mean value theorem is about the rate of the initial temperature change. So that usually is an indicator, and if you read this language here, the stuff that I've highlighted kind of in the purple color is the indicator that this is why it's the mean value theorem. It does give some prior information up here that you denote that the f of t is a temperature and f prime of t is defined and continuous, which are two conditions where you need for mean value theorem to apply. And it does say that the average rate of change of 10.6, which I've illustrated here with my calculations. Therefore, the mean value theorem says that f prime of c, this c being some time between or in the first 20 seconds, you must have a instantaneous rate of change of 10.6 during that interval. So if you might be a little bit clearer for you, it's running a marathon. A marathoner ran a 26.2 mile New York City marathon in 2.2 hours, so we're dealing with miles over a time interval of hours. Show that at least twice the marathon runner was running at, once again, we got miles per hour. Probably an indicator of the mean value theorem. When you look at the solution here, the runner's average speed was that 26.2 divided by 2.2, and that gives me a result of 11.909. Therefore, the mean value theorem states that the runner must be going at least that speed at least once during that marathon. But here's the key to this one. When the gun goes off to start the marathon, the runner starts from rest. So if you look at the speed graph here, at the beginning, the marathon runner would have been running at 0, and at the end, they stop at the end of the race, he'd be running at 0 too. So if we're going to be talking about hitting this average speed twice, he would have had to increase his speed over that interval to get higher than 11.9 and then come back down to get back to 0 at least twice. Now, of course, he could have actually done something like this and hit it multiple times, but to get with that mean value theorem combined with a little bit of intermediate value theorem, he would have had to hit that at least twice, maybe more, but at least we know it's twice. So that's kind of a little explanation on the mean value theorem. Here's your lesson on 4.3 using derivatives for curve sketching. If you need to pause the video to rewind it and listen to me again if I say something, please do so. You'll find this lesson very similar to something you would have learned last year. I might have a couple different suggestions and styles of writing these kind of problems, but you're going to find a lot of this very similar. So as we begin, in the past, one of the most important uses of derivatives was to aid in curve sketching. Even though we usually use a calculator or computer to draw complicated graphs, it's still important to get an understanding of the relationship between derivatives and their graphs. I do have a help sheet on this that I'll hand out to you next time I see you. It basically clarifies all of the thoughts I have on the next page, but feel free to write them down too to kind of clear up. So these are things that you would have experienced last year also. So one of the first things is what does the first derivative tell us about a general curve? Well, if the derivative is positive, the curve would be rising in an upward direction, and if the derivative is negative, the curve would be falling in a downward direction from left to right. If the derivative ends up to be 0, you possibly are going to have a local maximum or a local minimum. For example, here are two curves where you have a derivative at the top here, slope of the tangent line being equal to 0, and a bottom or a minimum where the slope of the tangent line there is equal to 0. But the reason why I say possible is because you could have a situation kind of like a cubic function where you have just like a little leveling off here. And at this moment right in the middle here, you could have a slope of the tangent line at 0. So you have neither a minimum nor a maximum. But you usually do have these situations, but you have this rare one where you actually don't have a maximum or minimum. That's why it's called possible. What about the second derivative? Well, the second derivative, we've talked about this a little briefly in class, but if the second derivative is positive, the curve is concave up. Concave, I like to think about curvy, so curvy up. So this is an example of a curve or a concave up graph. If the second derivative is negative, your curve is concave down, like that. And here's another big one too. If y double prime is 0, you have a possible point of inflection, but you don't necessarily have one. Now, point of inflection is when the graph changes from concave up, like on this green part, to concave down, like on this little yellow part. And the point of inflection is that black line where concavity changes. So you have to be really careful though. The second derivative must be 0, but it must clearly change sign so that your graph changes from concave up to concave down or vice versa. Here's an example. Now, if I was going to graph y equals x cubed minus 3x squared plus 4, you could factor this. This is a kind of a complicated one to factor because there's no real great factoring methods to do that, so I'll just kind of have this one factored already for you. There are times where you'll have to factor them on your own, but I like this problem because it has this multiplicity of 2 here with the exponent of 2, so that kind of changes the graph a little bit, and we'll talk about that in a moment. So this one is already factored, so this might be a good possible multiple choice or even an FRQ problem. And our mission here is to find out where y is increasing and explain why. The y is going to be how you're going to detail the FRQs as to tell me why something's increasing. Find the extreme values, maxes or mins, and say why. Tell me when the graph is concave up and concave down, and of course justify that reason. And then try to find points of inflections and justify that reason. That's the why. So a couple bits of information about this graph. If you set this equal to 0, 0 equals x plus 1. And I'm running out of room here, so I have to go down. And x minus 2 squared. You know that each of these pieces could be 0, so x could be negative 1. And x can also be positive 2. So that tells us, it's going to be hard with this stylus I'm writing with here to put this on the graph, but I'll do the best I can. When x is 2, I'm going to count by halves on this graph to make it a little easier for me to draw with this little stylus I'm writing with. So if x equals 2, you got half 1, half 2. So here is around 2. And you got x equals negative 1, so counting by halves, that's approximately negative 1. And if you know this follows a cubic, so with the end behavior model, it kind of would go something like this. I already know this from my previous classes, that this is what the graph is going to look like. And I know that because you kind of studied this, that when you have a multiplicity of 2, there is a 0 right there, but it doesn't go through the axis, it just touches the x-axis. And when you have this function right there, it actually is going to go through the axis at -1. So that, I know that's what it looks like, and I could probably then answer all these questions, but when you're doing calculus, all these y's must be justified through derivatives. Let's continue on. So if they're asking you why something happens, we want to make sure we use an interval to explain that. And anytime you use intervals, you could certainly use like something like 0 is less than x, which is less than 2. But I like to write this in interval notation, and I just like to say something like 0, comma 2 with either parentheses or brackets depending on what I need. Maxes and mins and point of inflections are very important that you indicate you have a sign change of either the first derivative for maxes and mins and the second derivative for points of inflections. One of the most common mistakes students make is say, well, you have a minimum because the derivative is 0, or you have a point of inflection because the second derivative is 0. Be careful. You have to specifically talk about the sign change and what kind of change you have. Some students in their beginning writing on this stuff like to write like a 50-word essay. I'd like concise writing using math notation, which makes things much simpler. Know the difference between your answer if you're asked for an x or a y. The x is what location would a maximum or minimum occur at, or what time would a maximum or minimum occur at. And if they wanted a y value in the problem, they'd ask something like, what is the highest point of the ball would reach, or what is the farthest right the particle would reach, things like that. We'll detail the first and second derivative tests in a moment, and we'll talk about this too in a brief moment. So here's our same problem. What you're going to do here is you're going to take the first derivative of the function to start with. So this original function right here, you take the first derivative, because the first derivative will analyze increasing, decreasing, maxes, and mins. That's the path that you're looking for right here and the first derivative tells you this story. So first derivative is 3x squared minus 6x, and then you want to find when this is 0, and if this is a no calculator problem, the best way to do that is to factor. So you take the derivative, set it equal to 0. You must show this work if you're writing an FRQ, because these are usually worth points. And the best way, obviously, is to factor. Now, there's different ways to do this. I divided through by 3, or you could have factored out of 3x. It doesn't really matter. It'll yield the same result. I decided to divide by 3 and factor out just a single x. So then I get an x equals 0 and an x equals 2. So this is the zeros of the second derivative. This means that these are possible maxes and mins, but I have to kind of check to make sure that they actually are. So my next step then, here's the same work from the last slide over here, just carried over. I'm going to try to use a chart to organize my thoughts. So you probably did these charts last year. They can be done in a little different fashion. And this chart I'm going to show you here is how you do the first derivative test. So the thing with charts is if you ever use them, they have to be labeled. So I need to know, are you doing the first derivative or the second derivative? And I also like the values here at the bottom to be labeled as x's too, so that I know if you're putting your x's on the bottom or your x's on the top. I kind of like them at the bottom. So the way I would do this is I would easily identify my zeros, which I already have, which are right here and right here. And then I'm going to check between the zeros. I'm going to check to the right of the 0, and I'm going to check to the left of the zeros to see what my behavior is. So I would pick something between 0 and 2, try to pick something very easy like 1. Now 1 could easily be put into this foiled out derivative, but it's probably easier to be put into its factored form. So in its factored form would be this, or if you kept the 3 with it, you could have the 3 there also. Remember, I divided through by 3 here. But I'm going to plug the 1 in here. So if I did that, I would have, I'll show you a little work on this one, y prime equals, substituting a 1 in, I got 1 parentheses 1 minus 2. Now I don't really need to do a lot of work here. That's why I like factored form, because it's not necessary to determine the numerical value of this. It's only necessary to determine if it's positive or negative. So I know this parenthesis is negative, and this thing out front is positive, so a positive times a negative is a negative. And I would do the same with a 3. So quickening that, if I put a 3 in there, and I put a 3 in there, 3 minus 2 is a positive value, and 3 is a positive value. A positive times a positive is a positive. And likewise, you can do the same thing with, say, negative 1 right here. And then that negative 1 would yield a positive value for y prime. Well, what does that tell us? I'm going to use green here. That tells me that in this alley, all the way to negative infinity, the first derivative is positive. Therefore, if I'm thinking about this graph, and I'm going to 0, 0 is in the x-axis here, you know that that function is going to be increasing, going upward. And then in this alley, from 0 to 2, you know, and 2 would be like right here, it's going to go down. And then you know, from 2 to infinity, it's going up. Now, do I really know how high it goes, how low it goes? I kind of have this idea because I understand about multiplicity of the original graph, but if you didn't know that, you wouldn't really know how high and low these go unless you substituted these values into the original function. So carrying out this, this is a summary kind of what things tell me. This is a different way to substitute things in. So this look and this take on things, we're substituting them into the 3 times x squared minus 6 times x. But like I said, that's perfectly acceptable to do that. But I like to use factored form because it's quicker and easier in my brain. Now, basically, visualizing this all again in summary about my increasing, decreasing, I didn't quite make the connection specifically to maxes and mins, but once again, you know you're going to have a maximum at 0, and I know that because the first derivative changes from positive to negative, so I know that that means increasing, decreasing after that critical point of x equals 0. And when I get to 2, I know decreasing and I know increasing behavior. Therefore, I can surmise that it's going to be a minimum. Now, as I finish this out, these wording, let me do one at a time, is where I mentioned earlier that you can't get too wordy on things. You're going to be asked for why is there a maximum or a minimum. If you read through this, what I have here, you notice that there's a lot of math notation in my explanations, using intervals and using greater than and less than symbols and things like that, as opposed to writing a long 50-word essay. So as you read this little first line here, it basically says that there's a local maximum, and I knew that, kind of like right here, at x equals 0. This is a point because of the context clues about it. So there's a local maximum at x equals 0 because the derivative, and use a specific derivative, don't just say the derivative. This is using the function y. So I said y prime. Y prime is positive from negative infinity to 0. This is there, an interval right there. And y prime is negative from 0 to 2. And that defines a local maximum when the derivative changes from positive to negative. And notice I used intervals. Now some people will say this in a huge amount of words, but you don't have to do that. One other comment that I have to make here is How did I know that y was 4? Well, if I substitute 0 into the original graph, 0, 0, 0, and 3 times 0 squared, blah, 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 plus 4 is going to give me the number 4 over there. So that's how I knew that it was an ordered pair of 0, comma 4. And then a local minimum at 2, 0. And once again, how did I know that the 2 had a 0? Well, if you wanted to, you could plug in 2's for your x's into the original function. Right up here. And just reading through that, there's a local minimum at 2, 0 because y prime change for all x in 0 to 2, and y prime is greater than 0 from 2 to infinity. So you could definitely say that in a lot of different ways, but know the difference that, I mean, the one thing I want to catch your eye is, I'll highlight these in yellow, this is a point, and this is an interval, and then kind of you look over the words around it. At means a point, and in would indicate an interval, even though they look very similar. Some people get hung up on, okay, well, do I have to say 2 comma 0? Do I have to use like brackets or parentheses? We'll talk about that in class. Right now, I do not want you to worry about parentheses versus brackets for the interval when you're talking about like an interval from 0 to 2, things like that. All right, almost done here, except for the second derivative test. So let's analyze this second derivative test. What the heck is a second derivative test? The second derivative test says, kind of up here, that if the first derivative is 0, you know you'll have a maximum, a minimum, or one of these neither things. Well, you know what you could do? You could analyze the second derivative, and if the second derivative is negative, like it is in this first statement, then that means concave down, therefore you have a maximum. And if the second derivative is greater than 0, that means it's concave up, and therefore you have a minimum. So this is helpful when you don't have, you can't really check intervals, but you can check a specific point. I'll give you an example from something that was given on the AP test. This is from an old AP question. This is where you're given an actual dy dx, like a slope of the tangent line, equals 2x plus y, a formula for the derivative. And the question is the point 1, negative 2 a relative maximum, a relative minimum, or neither? See, the problem with this is if you wanted to check an interval around 1, you might check like x equals 0. Well, how are you going to check x equals 0 in the derivative because it's dependent on y? You can't really do that. So the only thing you can do is check a point. So if you have a point, or if you're given a point, you have to use the second derivative. This is how they force you into using the second derivative test. And then there's a little more here. It says find the second derivative, and it equals 2 plus the first derivative. Since we already knew the first derivative is 0, then we know that these things is positive, and it's increasing. So this, I just wanted to give you an example. You don't have to really get into this too much right now in terms of this specific problem. Let me erase this stuff here so you can see this if you want to pause and take a look at this a little bit more specifically. But I wanted to highlight this one for you just to kind of show you when do you have to use the second derivative, because I find most students are using first derivative, first derivative, first derivative. So for something like this, you would take this ordered pair and you'd substitute it into the first derivative. So you'd get dy dx equals, substituting in a 1, you get 2 times 1, which is 2. And then the y is negative 2, and you get 0. So that means I've got either max, min, or neither. So the second derivative is going to be, 2 plus, well, whatever the first derivative is. And the first derivative is this thing, and I've already evaluated that. It's 0, so it's plus 0. So this is going to be equal to 2. So hey, guess what? I know what's happening here. Because I get a 0, I either have this, this, or this. But since the second derivative is a positive number, positive 2, then I know that it's concave up, so I've got a minimum at that point. How does this apply to our previous example we used? Well, take the second derivative, you get 3x squared minus 6x. You then could use the second derivative test, and that means you just basically take the second derivative, so 6x minus 6. Now remember when we got that 0 initially and we had to check the interval around 0 to figure out if it's an actual max or a min? Well, now I don't really have to check 1 and negative 1 to check positive and negative of the first derivative. I can just check the second derivative. So if I check the second derivative here, all I have to do is plug in 0 and you get negative 6. Likewise, I could do the same with 2. Take a moment to read through this here, and that's how you would justify a second derivative. Point of inflections is the last thing I want to touch on, and point of inflections is when a graph, in summary, remember, changes from concave down to concave up. And this little gap here is the point of inflection. It wouldn't have a gap, of course, but I'll put it in black so you can kind of see what's happening. Or, of course, you could go vice versa. You could have concave up to concave down, where you have a point of inflection in the center there. So they look very similar, except they are a little bit different. This one has a horizontal tangent line, where this one has a vertical tangent line. So we have to check those. So once again, you take the second derivative. Here's all your work for the second derivative. Pretty simple, straightforward. And you once again can make a little chart. So looking at our chart, we labeled this as y double prime. I also like to put the x on the bottom because some of you like to put your x's on the top, which are perfectly acceptable. If you do not label your sign charts, that's a problem. Usually the graders have a problem with that, so make sure you label them. And then checking the 0, you get negative 6, and checking the 2, you get 6. So what does that tell us? That tells us we have a negative to the left of 1, and that's why I checked 0. Could I have checked 0.9? Of course I could have. Why, though? When you knew that the only 0 is at 1, and you could check anything to the left of 1, choose easy numbers. And then this is positive. So I know I have a concave down situation, followed by a concave up situation. So it's likely to look like this, and it's likely to have a point of inflection at that moment in time. This is a final chart which actually digitally draws the graph that we originally knew what it was all about, because we knew a little bit about multiplicity and zeros and things like that, but now we know exactly how curvy it is and things like that. You can see this chart lists your x values right here, and then it tells you your y values, which you could have plugged in easily, and those are just ordered pairs. But what does this column that I'm circling in green represent? That represents positive numbers. You have increasing behavior. So like the 9 would be increasing, and this 9 would be increasing, and then the negative numbers here would be the decreasing behavior. And then likewise, this stuff right here is going to give me my concave up. So the negatives are here, so concave down. Whoops, sorry, I should have stopped right at that point of inflection. And then my positives down here are going to be concave up. So that basically is a summary of everything we've gone through. You did all of this last year, like I said, but I have a little take and a way of summarizing, and I feel like most people coming into this class are weak on the second derivative test, so I wanted to spend some time. This is your assignment, which is your regular assignment right off of that assignment page. So good luck, work on it in class today, and we'll see you next class. Thank you very much.